Hey guys, this is Mrs. Rooker. I'll be doing videos 10, 11, and 12 with you. So pause the video right now and do the review problems. And when you unpause, I'll have the solutions up. Okay, here are the solutions. For the first one, for number one, I would just see which of these does not simplify to be the same thing as 256. So I just used my calculator and did 2 to the 8th power is 256. 8 to the 3rd power was not 256, so our answer is C. And then number 2, that's going to be an exponential growth function. So it's exponential growth, but it's got an asymptote down at -4. So there's an asymptote down here. And I don't really care what the graph looks like other than the fact that it's exponential growth and it's going to be above that -4. So that's why B is our answer. All right, so today we're going to do applications, and pretty much all of these problems can be done using your graphing calculator, the same exact method that we did for last unit when we did word problems. But because this is the log unit, I'm going to show you guys how to solve each of these using logs. So we're going to solve these algebraically. I might also show how to do some of them on the graphing calculator, but you are going to want to know how, or you are going to be required to know how to do these algebraically, meaning solving using logs. So the first one, scientists experimenting with the effects of a new antibiotic on a particular bacteria population found that the population of bacteria can be modeled by the function f of t equals 2000 times 1 minus 0.25 to the power of t, where t is the time in days the antibiotic is taken. Scientists have also discovered that this antibiotic can only be taken for a maximum of 5 days before it is considered harmful to the patient. In order to consider the person cured of the bacteria infection, an initial population of 2,000 bacteria must be reduced to less than 200. Is it possible to cure a person with the new antibiotic? So I guess I should have been highlighting as I go. But here's some key information. They can take it for a maximum of 5 days, so no more than 5 days. And in order to be cured, an initial population of 2,000 needs to be reduced to less than 200. So we want to see if it can reduce to 200 in 5 days or less. So I'm just going to plug into the equation. Oops. We want it to start with 2,000, which is already in the equation, but we want it to reach 200, or really less than 200, but we'll see how long it takes for it to reach 200. And then I'm going to do 1 minus 0.25. I'm actually going to simplify that. 1 minus 0.25 is going to be 0.75. Just makes it a little easier when we're solving to the power of t. And we need to solve for t. First thing we do when solving for something that's in the exponent is we try to isolate the base. So we're trying to isolate this. We need to get rid of everything that isn't being raised to the t power. So I'm going to get rid of the 2,000 first. I'm going to divide both sides by 2,000. I'll be left with 200 divided by 2,000 is going to be 0.1. All right, and then at this point, in order to solve, I need to either convert to log form or log both sides. I think I'm just going to log both sides. And the whole point of that is I can now use my properties of logs to take the exponent and bring it to the front. So this is now going to be log of 0.1 equals t times log of 0.75. And the whole point of that was to move the t out of the exponent so that we can solve for it. So now it's t times log 70, or log of 0.75. So now I'm going to divide away the log of 0.75. Divide that on both sides. Log of 0.75. I should be writing it in parentheses like that. Now I'm going to type that into my calculator to solve. So turn it on, log, and I could have done natural log. I just chose to do common log, but you can do either one. Log of 0.1 divided by log 0.75 gives me about 8. So t is about 8, which means it would take 8 days for someone to be cured. But if we read this kind of key information right here, they're only allowed to take it for 5 days. So no, they will not be cured. Okay. We could have done this by typing this into our graphing calculator. I think I did this already. Oops, it erased from my graphing calculator. Just type it again. 2,000 times 1 minus 0.25, which becomes 0.75, or you can write it the other way, it doesn't matter, to the power of t, or in this case we'll put x. Then I look in the table at how long it takes for it to reach 200, or really below 200. It's going to take a little over 8 days to get below that 200 mark, just over 8 days, which is the same as what we got when we solved it algebraically. All right, moving on. 3 people invest in the business. 3 people in the business club are competing to see who can double their investment in the shortest amount of time. Each person starts with an initial amount of 3,000, but they can choose different investment scenarios. Who will double their investment first based on the following information? So when I look at this, I can kind of estimate that it's probably going to be the person with the highest rate, because the higher the rate, typically, the quicker you're going to earn money. That has a bigger impact than how often it's compounded. But we're still going to do the algebra here just to confirm that theory on this one. All right, so we are starting with 3,000 and we're trying to see how long it takes to double. So in this first scenario, starting with 3,000, that's our principal value. The amount we want it to be is 6,000. I'm trying to see how long it takes to double. Then it'll be 1 plus, in this case the rate is 6.2%, so move the decimal over 2, that'll be 0.062, over n stands for the number of times per year that it's compounded. So if it's compounded quarterly, n is going to be 4 times per year. And then to the power of 4t. And we need to solve for t. So same thing, we're going to get, we're just going to simplify. We're going to get this by itself and then log both sides. So I'm going to get rid of the 3,000, divide both sides by 3,000. I'm not going to take the time to write all that. If we divide 6,000 by 3,000, we're going to get 2. And then I'm going to simplify this part here really quick. That's going to be 0.062 divided by 4 is 0.0155. So this will be 1.0155 when I simplify everything that was in that parentheses. And then that's still going to be to the power of 4t. Now we log both sides so that we can use our properties of logs to bring the exponent into the front. So I'm going to do natural log this time. It doesn't matter if you use natural log or common log. So we'll have natural log of 2 equals, now I can bring the 4t in front. So it'll be 4t times natural log of 1.0155. Now, to get t by itself, I'm just going to divide by everything that's being multiplied by t right now. This is 4 times t times natural log of 1.0155. So I'm just going to divide by 4 times natural log of 1.0155 on both sides. and that will cancel out everything except for the t on that side. So what I'm going to type into my calculator is, let's quit this, clear, natural log of 2, and then I'm going to divide that by 4 natural log, oops, I didn't mean to do that, delete, natural log of 1.0155, close parentheses. And I got 11.266 years. All right, we are going to do that exact same thing, except we now have a different rate and a different n value. It's now going to be compounded daily, and our rate is 5.9%. So same thing though. I'm going to skip this step. No, that's okay. I won't skip. I'll show all my work. 6,000 equals 3,000 times 1 plus our rate is now 0.059 over compounded daily. There are 365 days in a year, so it's going to be 365 to the power of 365t. Divide both sides by 3,000. We'll get 2 equals, and then I'm going to simplify again what's in these parentheses. I'm going to do 0.059 divided by 365, and then do 1 plus that answer, and I got pretty ugly decimal, 1.0001644. I'm going to keep that stored in my calculator so that I can be pretty precise with my answer. 365t. The more decimals I have on there, the more precise I'm going to be. At this point, I now log both sides. I can use natural log or common log, doesn't matter. The whole point of that is so I can now use my exponent rule, or my log rule, and bring that exponent in the front. So it'll be natural log of 2 equals 365t times natural log of 1.000161644. And then to get t by itself, I'm going to divide both sides by 365 natural log of 1.0001614 or 161644. All right, and then type that into my calculator. It's just getting a little tedious. These are a little bit long, but same process almost every time. Right, natural log of 2 divided by, I'll just do divided by 365, enter, divide by natural log of 1.000161644, and I got 11.749 years, which means this guy, this guy is still winning, because he or she doubled their money first. And then we'll do the last one, which should be a little easier, should be a lot easier, because we're compounding continuously. So we're using the continuous interest formula, which is different. So we still are starting with $3,000. That's our p value. But we want to end up with 6,000, so those numbers didn't change. Times e to the rate this time is going to be 0.05757 t. Still, we want to get the base and the exponent by itself, so we want to get rid of the 3,000 first. So divide by 3,000 first. We get 2 equals e to the 0.057t. And then solving this one's going to be easier than solving any of the others because we have natural base e. I'm just going to natural log both sides. And remember, natural log has a base of e. This is an exponent base e. Those will cancel each other out. And we'll be left with natural log of 2 equals 0.057t. And our final step is just to divide away the 0.057. And that'll be our answer for t. We'll do that on a calculator really quick. Natural log of 2 divided by 0.057. Make sure to close your parentheses on the natural log so it doesn't think that the 0.057 is part of that. All right, and we got 12.16 years. So that one took the longest, which hopefully makes sense since it had the lowest rate. The higher the rate, the quicker your money is going to grow. So this guy is the winner for who doubled the quickest. All right, I gotta hurry up because we've got several more things we need to do. All right, an exponential model for the function, or for the population in millions of Russia since 2016 is given by the following equation. What was the population in 2016? Well, they told us this started in 2016. So the population in 2016 is just the principal value. That's always the number in front of, or it's your A value or your P value, depending on which formula you're using. I guess we'd call that our P value there. So it's going to be 142.9 million. All right, is the population increasing or decreasing? Well, if we look at this equation, there's a negative in the exponent, and whenever we have e to a negative exponent, that's decay. So if we have decay, it is decreasing. All right, what will the population be in 2012? So that's 6 years later. So we are going to plug 6 in for t and solve this. I'm going to do it. I'm going to do this with the graphing calculator just to save us a little bit of time so this video isn't forever long. And since we're just solving for t, actually no, I'm not doing the graphing calculator. I'm not going to take the lazy way out. We want to see what the population will be 6 years later, so we'll do this algebraically. 142.9 e to the negative 0.004 times 6, because 2012 is 6 years after 2006 when we started. I'm just going to type this into the calculator. I could do this into the graphing part, but I'm just going to do it. I am going to do it. No. Keep going back and forth, typing it into the main part since I'm doing these algebraically. 142.9 times e to the power of negative 0.00, yeah, 2 zeros there, 4 times 6. And I got 139.5 million, which hopefully makes sense. Whoops, that's the answer to this one. 139.5 million, which hopefully makes sense because we decided that the population was decreasing. All right, when will the population reach 3 million according to this model? Well, last unit, what we would have done is plug this into the table function of our graphing calculator, and we would have scrolled to see when it hit 130 million, but we're going to do this algebraically since we're in the log unit. So we want to see when it's going to be 130, and we're just going to plug that into the formula, 142.9 e to the negative 0.004 t. We want to get e to the negative 0.004 t power. We want to get that by itself, so we're going to divide by the 142.9 first. I'm just going to leave that in fraction form so that we don't have an ugly decimal. So this will be 130 over 142.9 equals e to the negative 0.004 t. All right, anytime you're trying to solve and you've got base e, you're going to cancel out that base e using natural log. So we'll end up with natural log of 130 divided by 142.9 equals negative 0.004 t, and then you'll divide both sides by negative 0.004 to get t by itself. So what we'll type into the calculator is that. So natural log of 130 divided by 142.9 we can put equals or not, and then divide by 0.004, negative 0.004, and I got 23.65. So I could put about 23.7 years later. Or if we want to put a year, that would be, well, 23.7 years after 2006. So 2006 plus 23-ish years later, sometime in about 2029. All right. 2 more problems, then we're done. I'll try to bust through these. Rachel deposits $331 into an account that earns 3.31% annual interest compounded continuously. And how many years will it double, triple, round to the nearest tenth? So 331 is the initial amount. E to the R is going to be 0.0331 t. And we want to see how long it's going to take to double. Well, double 331 is going to be 662. But we're going to get rid of the 331 to begin with anyway. We're going to divide both sides by 331, and we're going to get 2, because this was double this. So it's going to be 2e to the 0.0331 t, and then I'm going to natural log both sides to cancel out the e. And last but not least, I will divide away 0.0331 to get t by itself. So we'll type that into my graphing calculator. Natural log of 2, divide that by 0.0331, and I get 20.9 years. So 20.9 years to double. And then obviously it's going to take more than that for it to triple. So in order to triple it, what would that be? That would be 993 is how much money we'd want in there. So 993 equals 331 e to the 0.0331 t. But the first thing I'm going to do is divide by 331. Since 993 is 3 times 331, this is just going to be 3 equals e to the 0.0331 t. So we didn't even really need to know what the principal value was or anything, because If we want something to triple, we just put 3 here. If we want something to double, we just put 2 there. If we want something to quadruple, we put 4 there. All right, to get e by itself, or sorry, not to get e by itself, but to cancel e out, we natural log both sides. That'll cancel. To get rid of the 0.0331, we divide by 0.0331. And this is what I'll type into my calculator. Natural log of 3, divide that by 0.0331, and I get 33.2 years to triple. All right. Find the doubling time of an investment earning 3.25% annual interest compounded continuously round to the nearest tenth. So, like I was just saying in this last one, I didn't need to know what the principal value was, what the starting amount was, because if I want something to double, I just put a 2 over here. If I want something to triple, I put a 3 over there. So, find the doubling time of an investment. So, since I want it to double, I'm just going to put 2 e to the 0.0325 t. Because I want it to double, I just put the 2 there. I didn't need to know the principal amount. Now I natural log both sides to get rid of e. Last but not least, to get rid of the 0.0325, I divide by 0.0325. Type into my calculator natural log of 2 divided by 0.0325, and I get 21.3 years because it said around the nearest tenth. 21.3. Alright, that is it for this video. Hopefully the next one will be a little quicker. Thank you guys. Have a good one.